Hi my dear students, I am Sunira from Department of Physics, Government College, Madapalli. In our previous lecture, we learned about the mathematical expression for a pulse. We derived the expression for pulse as psi of t equal to a of t cos omega avt. Omega av represents average angular frequency. Similarly, the amplitude a of t is given by the expression a0 sin n delta omega t by 2 divided by n sin delta omega t by 2. In this equation, we know that if this capital N is very large, delta omega is very small. So, in the contrast, for large n, that means n tends to infinity, delta omega tends to 0. That means capital N is very large, huge number. In that context, this frequency difference delta omega nearly 0, tends to 0. So we can modify this expression such that we know that n minus 1 into delta omega equal to the frequency band. That is, this is equal to omega 2 minus omega 1. For large n, this expression is approximately equal to n delta omega. So, for very large n approximately equal to n minus 1. So, n minus 1 into delta omega approximately equal to n delta omega, which is equal to the bandwidth or frequency band of delta omega. Okay, so we can use this equation in this expression. Similarly, in this equation, you can see that in this denominator, here this term delta omega t by 2, sin delta omega t by 2. Here this delta omega is very small. So this term sin delta omega t by 2 approximately equal to delta omega t by 2. So sin delta omega t by 2 approximately equal to delta omega t by 2 because of this condition, delta omega tends to 0. So we can use these expressions delta omega t by 2 and delta omega in this equation. So we get a of t as a of t equal to a of 0 by n, then sin n delta omega t by 2. So sin delta omega t by 2 divided by next sin delta omega t by 2. This term approximately equal to this argument delta omega t by 2. So you can substitute here delta omega t by 2. Further simplifying you get a of 0 sin delta omega t by 2 divided by delta omega t by 2. So the expression for pulse takes the new form psi of t equal to a of t cos omega avt with amplitude a varies like this: a of 0 sin delta omega t by 2 whole divided by delta omega t by 2. So we get the expression for pulse as equation of this form. Suppose this is equation 3 with amplitude is given by this expression a of 0 sine delta omega t by 2 by delta omega t by 2. Together this equation represents the mathematical expression for a pulse. Now we can check our previous equation of the pulse such that summation of harmonics. So that equation is written as psi of t equal to a into cos omega 1 t plus cos omega 1 plus delta omega t plus cos omega 1 plus 2 delta omega t plus cos omega 2t. This equation is familiar to us in our previous lecture, where we start with the superposition of a number of harmonics starting from omega 1 frequency to omega 2 frequency. Each frequency component separated by a frequency delta omega. So first harmonic is with the frequency omega 1, next harmonic with frequency omega 1 plus delta omega, next one with frequency omega 1 plus 2 delta omega up to frequency omega 2. This expression is familiar to us. We derived it earlier. Now we can use some substitutions here. Here there is amplitude A. So we already found that A of t equal to A of 0 by n. This equation is derived earlier in our previous lecture. So we can use here this expression. Suppose we multiply both sides, both the numerator and denominator with delta omega. Then you get the expression as A of 0 by delta omega. Okay. Now you can substitute this expression A of 0 delta omega by delta omega in the expression for the superposition of different harmonics. So we can check the expression now. Now psi of t takes the new form replacing this A with this expression. So A of 0 by delta omega, then delta omega cos omega 1t plus cos omega 1 plus delta omega t plus etc. plus cos omega 2t. Now you can see that here the amplitude A is replaced with this expression and we get an expression like this for our superimposed wave or pulse. What's new in this expression? Here there is delta omega. We already found that for very large n, this frequency difference is very small. That is, it is nearly equal to 0. That means this frequency distribution is continuous from omega 1 to omega 2. So we can replace this summation with corresponding integration. Hope that you get what we have to do now. Here our equation is a summation of different harmonics. But each harmonic differ from its neighbor frequency by a very small amount, delta omega. This delta omega is nearly 0. That means any equipment cannot resolve these nearby frequencies. So we can assume that our frequency distribution is continuous from omega 1 to omega 2. So we can replace this summation with a corresponding integral. I can write the integral here. Now transforming this in summation to its corresponding integral, psi of t equal to a of 0 by delta omega, this part, then comes integral. Integration starts from omega 1 to omega 2. So lower limit omega 1 and upper limit omega 2. Integration is over this delta omega. This is discrete, this is nearly 0. For the integration purpose, it is replaced with continuous varying omega d omega. Then comes cos omega t. So, the expression for the pulse, mathematical expression for the pulse is obtained as a continuous superposition of harmonics as shown this equation. This is equation 4. So, we get the expression for pulse in the form of an integral. The integral is given here. What is the peculiarity of this integral? That is what we have to check now. For that, consider the Fourier integral. That means any non-periodic function f of t can be expressed as summation of sine functions and cos functions, or any non-periodic function can be expressed as continuous superposition of harmonics of the form. I can write here the expression. Let our function is f of t. F of t is non-periodic. F of t is non-periodic. That means this f of t can be expressed as continuous superposition. So, integration from 0 to infinity a of omega sin omega t d omega plus integral 0 to infinity b of omega cos omega t d omega. Okay, this equation is called Fourier integral. Fourier integral of a non-periodic function f of t. Here there are two terms. This is represent continuous superposition of sine functions, and this part continuous superposition of cos functions. These coefficients are called Fourier coefficients. A of omega and b of omega are called Fourier coefficients. A of omega and b of omega, they are called Fourier coefficients. Okay. Now we can define these coefficients a of omega and b of omega such that a of omega equal to 1 by pi integral minus infinity to plus infinity f of t sin omega t dt. Similarly, b of omega equal to 1 by pi integral minus infinity to plus infinity f of t cos omega t dt. This integral of a non-periodic function f of t. This is a mathematical theorem. Any non-periodic function f of t can be expressed as a continuous superposition of sine and cos functions. So there are two coefficients, a of omega and b of omega. They are called Fourier coefficients. A of omega is obtained from this expression 1 by pi integral minus infinity to plus infinity f of t sine omega t dt, whereas b of omega is given by 1 by pi integral minus infinity to plus infinity f of t cos omega t dt. Now, what is the role of this integral here? You can just check this expression. Suppose this equation is equation 5, our Fourier integral. Now, you can compare this equation with our equation for the pulse, equation 4. Any comparison, any similarity in these two equations? In equation 4 and equation 5? Yes, you can see that here the equation contains the second part, cosine series. This equation 4 represents continuous superposition of cosine functions. Frequencies varies from omega 1 to omega 2. In this integral, the frequencies lies from 0 to infinity. So, we can compare these two equations, equation 4 and 5. From the comparison, you can see that A of omega equal to, what is A of omega in this context? Here there is no sine integral, no integration over sine. So, A of omega equal to 0 for all frequencies, right? Now, what about B of omega? Yes, there is B of omega because cosine series. But B of omega equal to A of 0 by delta omega for omega lying between omega 1 and omega 2. A of 0 by delta omega for omega lies between omega 1 and omega 2. 0 otherwise. Right? That means if this integral runs from 0 to infinity up to 0 to omega 1, our coefficient is 0. So there is no integral. Then from omega 1 to omega 2, this coefficient b of omega equal to a of 0 by delta omega. So this integral is there. After omega 2, integration runs from omega 2 to infinity. There again the coefficient goes to 0. So the expression for pulse, equation 4, exactly looks like a Fourier integral. So this expression is called the Fourier integral form of the pulse, which we have discussed in this contest. Hope that all of you get what we have done here. We solved the expression for pulse, simplified the expression for pulse and comes to a simple equation in the form of a Fourier integral. So, we can move on to the next section. So, we can learn next what is the frequency spectrum. For that, frequency spectrum. The Fourier coefficient versus frequency is called the frequency spectrum of a function. That means if we plot a of omega versus omega and b of omega versus omega, those plots are called frequency spectrum omega versus omega and B of omega versus omega. These together called frequency spectra. Frequency spectra. So now we can plot the frequency spectra of the pulse, which we have already written in terms of Fourier integral. Okay. So now consider the pulse which is of the form this is a pulse. Suppose this is the pulse represented by our function psi of t. Here there is an envelope like this. This envelope represents the amplitude A of t. Similarly, suppose this amplitude becomes 0 at t equal to t1. Similarly, here is minus t1 where this function goes to 0. This amplitude goes to 0. So, this pulse has a finite value in between minus t1 to plus t1. Okay. Here you can see that the amplitude oscillates such that sometimes it is very low value and sometimes it is very high value. So we normally take the time duration of the pulse such that half of its time interval. So suppose this is the major portion of the pulse lies in between this region. You can represent this time duration as delta t. Okay, so this is corresponds to the half of the time interval which the pulse takes. It has maximum value, 40% of its maximum value lying between its here in this region. This is called the time duration of the pulse because below this region its amplitude loses considerably such that its amplitude never regains its maximum value again. At this point, at t equal to t1, all frequency components uniformly distributed in relative phase 2 pi. We already found in our rotating vector diagram. Then the frequency components never regain its maximum value again at t equal to t1. In between this time interval, its value, its amplitude varies less than the 40% of its maximum value. Okay, now we can plot this frequency spectrum of this pulse. We already found that A of omega equal to 0. So we don't want to plot the graph here because A of omega equal to 0. But B of omega varies such that B of omega has a definite value A0 by delta omega in an interval like this. This interval, this value is represent A of 0 by delta omega. This is omega, this value is omega 1 and this value is omega 2. So frequencies lie between omega 1 and omega 2. This amplitude is A of 0 by delta omega. So this represents the frequency spectrum of psi of t, which we already derived. Hope that you get how to plot this frequency spectrum. There are two coefficients in the Fourier integral. Those are called Fourier coefficients. In the special case of this psi of t, its A of omega equal to 0. because its representation has only one integral which contains cos omega t. So here the coefficient is only b of omega. This b of omega equal to 0 up to omega 1 and greater than omega 2. But it has a finite value, constant value a of 0 by delta omega in between omega 1 and omega 2. So this spectrum looks like a square. So it is called square spectrum. This frequency spectrum is called square spectrum because its shape looks like a square. Okay, so I think that you got how to draw a frequency